Bharati.
Good to see you as well.
Okay, so I'll just introduce myself if that's okay, or yeah, I'll just shortly introduce myself and then we move to the lecture. And so my name is Luna Bharati. I did my PhD 20 years ago. I mean, so it's been a while. I was just counting this morning because I usually just write over 15 years, but I need to update my CV now, and also realized I'm getting older. But yeah, I did my university studies at Iowa State University in the US. I did my PhD in Germany, and then since then I've been working um, uh, in various countries, not just in Germany. So before I joined this current job, I was a principal scientist with International Water Management Institute, IMI, for around 16, 17 years. And this current job I joined about a year and a half ago, and I am the head of education and research at this small institute. And yeah, I'm a hydrologist by training, so the lecture today will be very watery. So just a couple of slides about where we work. So the institute is called International Center for Water Resources and Global Change, ICWRGC. It's like the acronym is impossible, but anyway, we have to live with it. So it was established by the German federal government in under the auspices of UNESCO in 2014. So we're what they call a UNESCO Category 2 center. So we're paid by the German government, but we're part of the UNESCO family. And we also are the secretariat for the WMO hydrological program. And we're funded by the Foreign Office and various ministries in Germany. One key activity, or one of the core activities we have at the center is to host these global data sets. So we have the Global Runoff Data Center, which has data. I don't know if some stations even have data starting from the 1800s, and so this data center is, so we're part of the German Federal Institute of Hydrology. And so this Global Runoff Data Center is part of VFG since 1988. So so it's flow data, no river data. So if any of you need river data from various, I mean, if you look at Southern Africa, you see the first the first picture here, it's blue. So that indicates that there's quite a lot of data. Red is when there isn't much data. So Southern Africa, there's actually quite a lot of data. We also host the GEMS water data, which is water quality data. And here also Southern Africa, there is some data, so water quality from rivers. We're trying to also integrate groundwater quality data. And we also started hosting this global soil moisture network and global soil moisture data. And so for some of you who will be modeling for your PhD work, some of the data from these data centers could be interesting for you. And it's all free and you can download at any time you want. Okay, so now moving on to the talk, and I think we have up till 12, so it's quite a long time. Okay, so it's quite a long time. So if you, maybe we should see if we need a break. Have you been having one break or two breaks?
Yeah,
or no breaks?
Maybe one break halfway through.
Okay.
Would be fine. Yeah.
All right. So maybe at like 10:15, 10:30, around 10:30, maybe we can have a break. And if I forget, please remind me. And I like to, I mean, so I have this associate professorship with the University of Bonn, where I teach as well. And I teach at the PhD program there at the center called Center for Development Research, and also a master's program. And I mean, I'm usually, very informal in the way I lecture, and I would like to make it quite interactive. So you please feel free at any time to raise your hand or speak up and ask me a question, because the point is that, it should be more of a discussion than just me lecturing. And so, yeah, so any questions you might have, or anything you might want to bring up, don't hesitate to stop. Sometimes it gets to be too much, and then we can't go through the lecture, and then I say, okay, please just listen for the next half an hour. But usually it's nice when we have sort of a discussion, right? And okay, so for the outline of the lecture today, I'll be talking about the global water context first, then a water cycle review. A review of the water cycle. I understand you've already had these lectures about the water cycle, the hydrological part, right? So I won't go into it too deeply, but I'll just review it a little bit. And then we move to climate change. Then we'll talk about climate change resilience and adaptation. And as I said, I'm a hydrologist by training. I've been working in the water sector my whole career. So the talk will be very much about water management also as an adaptation strategy. And I will also then talk about nature-based solutions as one form of adaptation. So there was a bit of a mistake in the poster. So the topics, I'm also familiar with modeling, but this lecture I won't really go into modeling. So I hope this is okay for you. And okay, so let's. So can everyone see the slides still?
It's not in slideshow, just standard.
Okay, so when we talk about global water resources, I hope you're seeing the same screen that I'm seeing. I don't know, it's a little bit confusing to me, but let's just go ahead. So global water resources, we have something called the James Bond formula. 0.00%, 007%, 007% of the world water amount is usable as fresh water. And how we calculate this is the total global water, 96.5% are in oceans.
Hello. We are stuck at slide number 4. They are not moving, so we are on the outline slide here.
Okay, you don't see the slide.
Yeah, it's the outline slide now that we are seeing.
Okay, but when I press this, does the animation work? Do you see a second column?
So we are just in slide 4 from our end here.
Ah, okay. I don't know why it's not working. But anyway, so.
Now it has moved to slide number 5.
Slide number 4. If you have some IT people that can help, that would be great. But if not, but you can still see all. Somehow the animation will not work in this mode. But if you can see everything, then I guess we can.
Suggestion, Prof.
Yes.
My suggestion is that you restart your computer. It will adjust in a better way.
Yeah, you think it might work if I restart my computer? Because it took me a while to connect to you. Or I can use my private personal computer if sometimes that works. So, okay, so let me do this. So let's just take a 5-minute break and let me figure out why this is not working. Okay, so I'll use my private computer and see if that helps.
Okay.
It is. What's happened here? The people are sleeping.
Dismissed.
Next time we call names. Next time we call names.
Don't worry.
You said next time you call.
We call names.
I want to call you, but no, I don't get your phone number.
Let's check.
Oh,
There are names, there are numbers there.
I forgot the rule. Yeah. Welcome. Welcome.
Yeah.
People are sleeping.
There is a problem with the she's trying something. Join.
Man of Jesus. How are you?
I'm good. How are you, my friend?
I'm fine.
You're fine.
Karagesho.
That's good. Mauricio. It's okay.
You are Karagesho.
No, I don't like it. No. I don't like it.
Don't forget it. Yeah. Yeah.
Yeah. Yeah, American one is that.
Camera is not. So can you hear and see me?
Yes,
Is this better?
can see you, can hear you.
Okay, so let me share here and see. Hopefully it will work. Um,
Wait, yeah.
so can you see my slides? But I mean, it's the same as last time, and it's somehow the camera. Okay, maybe this is my, somehow the camera isn't working.
You can see it. I can see you.
Okay, so the problem is when I go on, okay, so I'll go on presentation mode. Is it on presentation mode?
No,
I think it's still coming.
no.
So, I mean, I don't know what the problem is. I think the setup might be, so I think we just continue. And as long as you see, okay, so what do you see now?
Slide 5, global water resources.
Global water resources. Do you see one column or do you see the whole thing?
Whole thing.
Okay, so the animation doesn't work here either. But was it like this with the other lecturers as well, or somehow? Well, anyway, it doesn't matter. So I think we just continue. Okay, so yeah. So as I said, there's this James Bond formula, and well, anyway, if you can't see again, just let me know. I mean, in my computer, I see presentation mode. So yeah. Okay, so of the whole, I don't know, I hope maybe someone already showed you this slide. Have you seen this slide before? Yes, no?
No.
The other presentations.
Okay, it seemed the other time I could hear you better, so I'm just going to continue, but maybe I open up. Okay, just a minute. Yeah, so basically the amount of water we have on the earth, 96.5% is in ocean, and it's only 2.5% of it is fresh water. And of the 2.5%, almost 70% is in glaciers and ice caps, and 30% is groundwater. And so of the 2.5% of that water, it's only 1.3%, which is surface water and other fresh water. And of this 1.3%, 73% is in ice and snow, 20% is in lakes, and only around 0.5% is in rivers. So what I want to demonstrate just with this slide is that the surface water that we have on Earth is a limited resource. Right? So, and actually, if you look at the surface water in the last, 3.5% is in soil moisture and 0.46% in rivers. So there is more water in the soil than in our rivers. So this fact will become important when we talk about adaptation strategies. Okay, so can I move on to the next slide? Can you hear me?
Yes. Yes.
So it would be nice if when I ask you a question that you also respond. Is that okay?
Yes.
All right. So now the water cycle. I would like someone to come and explain the water cycle for me, because I think you've had this, right? So would anyone like to come forward and explain the water cycle? Otherwise, I pick on someone. So have you all heard of the water cycle?
Yes, we do.
Okay, so what is the water cycle? So someone, anyone?
I try explaining my.
But yeah, Patrina, is that Patrina? Or I can't really see. You're not allowed to. Should be one of the students, right?
I'm trying to explain water cycle in my vision point.
Okay, so please explain the water cycle to us.
I'm trying. Firstly, I think so. Most time we start for the water cycle for precipitation. this precipitation is when when the salt have infiltrations, some disinterceptation for the vegetations. After this, we have a movement in soil, some movements in the superfice. After this, this return again for sky and following this around you have temperature is like this.
Okay, perfect. Thank you very much. This is perfect. So, so these compartments, so what you see here is also part of the water cycle. So as our brave student already explained, I mean, you know, we can start wherever we want, but there's precipitation, evaporation, transpiration. So all these terminology are part of the water cycle. So the precipitation, then it recharges soil moisture, which also recharges groundwater eventually, but there's also overland flow. The overland flow then goes into the rivers and can cause floods, etc. So so this is my next slide. I hope you can see this. So when we talk about water balance, it's between the inputs and outputs, right? So it's usually inputs minus outputs is change in storage. And so the inputs, as we heard, it's precipitation. From your area, it could be groundwater that's coming in. And the outputs, what goes out of your system is evapotranspiration, as you know, evapotranspiration into the sky, as she explained, as in vapor form, runoff, and groundwater. And the difference is what is stored, the change in storage. So where is water stored? In groundwater, in soils, rivers, lakes. So this is a main concept of hydrology, and we also and climate change is affecting this whole water cycle. And how is it affecting the water cycle? It's accelerating the water cycle. So because of high temperature, evaporation is increasing. And this creates high intense precipitation events, storm events in certain areas, and drought events in other areas. So it's important to understand the water cycle and to remember that, climate change is affecting the whole water cycle and not just temperature or precipitation. It affects the whole water cycle. And so when we think about adaptation strategies or management, we also need to think about the whole water cycle and how we manage the whole water cycle, right? And so, so let's move on. I really wish everything was working. So this is again the hydrological cycle. We already, went through it, so I don't want to go again into this. But when we talk about water, there's the hydrological cycle and these natural water balances. But there's also the human aspect of water, because we also come and impact this water cycle. And so when we talk about water management, usually what we do, I'm sure you've heard of this before in one of the lectures, one or the other lecture, we have this water, we divide it into water availability and water demand or use. So when we think about water availability, so where is the water coming from? It's precipitation, directly, rain, rivers, reservoir, and groundwater, right? We don't really, and also soil water. I mean, I forgot to add that. So those are our sources of water. Are there any other sources of water that anyone can think of? Yeah, basically this is it. I mean, it could be different forms. We take this water and we store it somewhere in ponds or lakes or reservoirs, but in principle, this is, these are the sources of our water. And what about water use? Where do we use water?
Domestic purpose.
Yes. Okay, so that's right. So we have agriculture, domestic, industry, and then we also have, okay, so irrigation, livestock, mining, cities, industry, commercial, domestic, but we also have something for the ecosystem. So the ecology, the fish and the frogs also need some water, right? And so there's also that. And so when we look at a river basin, we have to think of all these things that interplay. So you've got your precipitation, runoff, going into rivers, but there's also extraction from the rivers for your water use, right? And so when we're actually modeling, we try to think of all these different components and quantify these components. So globally, most of the water, you probably know this already, is used for agriculture, almost 70%. But continent-wise in Europe, industrial water use is higher than agricultural water use. I mean, water withdrawal, water withdrawal from reservoirs and lakes, because here it's mostly rain-fed agriculture. And this water use or water demand, it's increasing. Why? Because population is increasing. So if you see this graph, you see water withdrawal, cubic kilometers per year, and then you see water withdrawal for industry, agriculture, municipal, etc. And then you can also see this black line, which is the population. And so everything increases according to the population growth. So that's mainly the main reason why water use is increasing. Okay, so that was more or less the global context I wanted to present to you, the global water context. Now we move on to the second part of the talk on climate change. Can we do that? Should I move on?
Yes.
Okay, so what is, I hope you can still see the slides. I don't know if it's readable or not, but yeah. Maybe in the break, I'll try to see if we can go to presentation mode somehow. But yeah, so climate change, I mean, this is just a review for you because I think you've already had lectures on climate change, but it's the change in pattern of weather and related changes in oceans, land surface, ice sheets. And so the difference between weather and climate is that weather is short term and climate is more this decadal, decadal patterns. And so certain gases such as water vapor, carbon dioxide, and methane observe infrared radiation flowing upwards from the Earth's surface and re-radiate it in all directions, causing the greenhouse gas effect, right? And this is causing mainly global warming. So this is just as a review for you, because I think Professor Fink already covered this, hopefully. And so climate change, how do we study the impact of climate change? So before we go on there, so can anyone tell me, how do we study, and please get off your phones, I can see you. How do we study the impact of climate change? So anyone can tell me, because you've had those lectures, I think, already, right? Please, someone from Professor Fink's lecture.
one of the ways is to get long-term hydroclimatic data, such as precipitation, maybe temperature, runoff, and any other related data. Then you carry out some trend analysis to see if at all there are any movements or deviations.
Yes, perfect. Yes, perfect. That's one way to look at all the data that has ever been measured. In some places, you find data from 100 years. In some places, it's just 10 years, but still you look at the trends and see if there is any change. So that's one method. What is another method? Has anyone heard of GCM and RCMs? Yeah? Yes, no?
Yes.
Yes.
Yes. So global circulation models, regional circulation models, these are projected, right? So there's these big modeling centers around the world, and they come out with these global and regional models that show climate change in the near future, mid-future, and far future. But this is simulated. It's not because what was mentioned before is actually measured change, whereas the other one is simulated change, right? So it's modeled. So another method, can anyone think of any other methods? The lady sitting in the front in orange?
I can't think of any.
Okay, so you see this graph here, a slide now?
Yes.
All right, so the first one is application of general circulation models, global and regional climate change models, right? So different parts of the world, there's these in Japan, in the US, European Union, UK, they run these big models and they project climate change. So these are then global GCMs and RCMs, trend analysis of past data, what was already said, and perception studies. I mean, we ourselves, we're talking about how hot it's getting, or how cold it's getting. In some places, even that the minimum temperature is increasing and the maximum temperature is increasing. So human perception of change is also a way in places where data doesn't exist. Human memory can also, so that's one way. And the last way
Dr.
is also,
there is an app, I'm not sure.
huh?
That seems to be up from one of your participants online. There's an online participant. Eileen's hand was up. I'm not sure if she wants to say something.
Okay, I can't see the chat somehow. So yeah, please just speak up if you want to say anything. So Eileen, please go ahead.
Oh, sorry, I was just answering while you were asking and I forgot to put my hand down because you didn't see me.
Okay. Oh, sorry, but I don't see the online participants so well because somehow, yeah, because of all these different modes. So if you want to speak, just speak up. All right. And I only see half of myself. Somehow my camera, the other computer, the camera was working better. Now it's better. Okay. Now it's a little bit better, I think. But yeah, and so perception studies, and the last one of the other ways is biosignals or biosignals, so phenological records. So one of the oldest is, the Japanese. They have this cherry blossom festival, right? And the monks in the Shinto temple, they were recording the days when the cherry blossom started since 1,000 years. And so looking at that, they found that there's shifts in when the cherries are blossoming. And so these are, and also, you know, in other parts of the world, you're beginning to see plants and insects where you didn't see them before. You know, they're moving they're migrating to different places because the weather is changing. And so this is also a way to try to document the impact of climate change. We don't have to always just limit ourselves to the biophysical data. There's also other ways of documenting climate change, and it's nice to combine these efforts. Okay, so that's, and when we look at temperature, I'm sure we've all seen this. So this is from the Met Office in the UK, and they've documented temperature increase. And with precipitation, it's not as straightforward as temperature. No, with precipitation, it's I mean, basically what I said before, rising temperatures are affecting this whole water cycle and increasing evaporation. And this increase in evaporation are causing frequent and intense storms, but also drying over some land areas where they're outside the storm lines, right? And that's also why we're seeing this intense climates of like increased storms as well as increased drought events, you know, increased intense events, and that's all over the globe. Okay, so so because of climate change impact, but also because of population growth and also the change in our lifestyle, there's rising water demand and increasing water scarcity. So at present, an estimated 3.6 billion people live in areas that are potentially water scarce, at least 1 month per year. And this could go to, you know, 5 to 6 billion by 2050. And if you look at these two maps, you see that Southern Africa is an area that has already been labeled as water scarce, and this will increase. And there's another graph that I show here. So water stress, I mean, water stress is also like water scarcity, but it's a broader term that includes also access to water, for example. And so by 2040, water stress will also increase. And of course, the MENA region, North Africa, Middle East, that's where it's highest. You know, but also Southern Africa, Australia, the United States. These are areas where water stress will become high. So the impact of climate change and water quality degradation is also increasing also due to climate change, but also because of industrial pollution. I mean, it's, you know, climate change doesn't just act on its own. No, it's being influenced by how we manage our water resources as well, or other resources, how we manage agriculture, industry, etc. So pollution is rising, and it will get worse. So if you look at these two, from 2000 to 2005, that was the base period. And here it shows pollution from low to high. And in 2050, pollution will increase also because of the intense events. So if there are floods and high flow events, then pollution is also increasing. There's also increase in water-related risks. I think yesterday you talked a lot about risks, but you know, there's all sorts of risks in the world, including earthquakes and volcanoes. But when it comes to mortality, human deaths, is the water-related disasters that are the most impactful. So droughts and floods kill more people around the world than earthquake and volcanoes and other disasters. And the disaster events are also increasing globally, and especially the water. Yeah. So this slide just goes to show water scarcity. And I think you might have seen this slide before, but water scarcity is measured not just from a biophysical perspective, but also economic perspective. For example, in much of Africa, the groundwater resources are vast, but because it costs something to withdraw water, pump the water out, the people in these communities, they face water scarcity, not because the physical water isn't available, but because they access the means to collect the water. And so I'm really sorry this thing isn't working. But now you see the slide on climate resilience?
Yes.
Okay, so what do we understand by climate resilience? So climate resilience is basically about coping and managing the impacts of climate change, right? And preventing those impacts from growing worse. So a low climate resilient society would be a low carbon society equipped to deal with the realities of a warmer world. So it's about both mitigation and adaptation. So can someone tell me the difference between mitigation and adaptation? Please go ahead.
I think mitigation is something when we applied measure before to reduce the negative impact that the people can have in the future. And the adaptation is something that we can do during the process to reduce the suffering of the people, or the way that the people can to live with the impact, negative impact that is happen. Actually, impact is before, and the mitigation is did before, and the adaptation is when the problem is happening.
Yes, that's perfect. Yes. So mitigation is basically you're trying to reduce your carbon footprint. So low emissions, right? And other ways to try to stop the progress of climate change and greenhouse gas emissions. And adaptation is how we adapt, how can we deal with the consequences of climate change. So adaptation and mitigation should go together. And with the Paris Agreement, I mean, all these countries, they signed a treaty, to promote both mitigation and adaptation. And of course, we're slow on both aspects. And so that's how it is. And so this lecture will primarily now focus on adaptation and not so much on mitigation. So climate change adaptation. So IPCC, the Intergovernmental Panel on Climate Change, their definition is what we already heard, which is completely right, the process of adjustment to actual or expected climate and its effects. So how do we, deal with intense precipitation? How can we deal with droughts? Because we know that there will be in the future more droughts. There will be in the future more storms. There will be in the future more flood events. So how can we manage our world, our systems to counter, yeah, impact these impacts that are coming from climate change. In human systems, adaptation seeks to moderate or avoid harm or exploit beneficial opportunities. For example, floods can also be beneficial, right? Because it brings a lot of water. I mean, it replenishes soil moisture, and the groundwater in that area. So floods can also be, and it also it brings a lot of fertilizer, fertilizes the soil and enriches the soil. So it can also be a positive impact, but we have to see it and use it as a positive impact, right? And in some natural systems, human intervention may facilitate adjustment to expected climate and its effect. So when we think about adaptation, there's the human, how we live in this world, how we need these resources, how they're changing, and what can we do to manage these changes, right? So, for example, how can we manage droughts? Or intense rainfall events. That's more focused on the human aspect. But us humans also need the ecosystems to function properly, because that's where we also get our food from. So fishing in rivers are only possible, or even oceans, are if there are fish around. The fish also need their ecosystems to be intact. So we have to also take care to also think of our environment and not just our human use. So water. Okay, as I said, because I come from the water sector, and we're all working in the water sector, and this is also IWRM PhD program. So we, us in the water sector, we always say, water is the teeth and claws of climate change. So that's how we feel the impact of climate change. No, so extreme events such as floods and droughts and tropical storms, changing variability in seasonal patterns of rainfall. So in a lot of places, there's this very this rainy season and dry season, and farmers have been managing or planning their cropping season based on when the rainy season starts, or the length of the rainy season. But this is now changing due to climate change. So we're feeling the impact through the water sector, river discharge. I mean, here in Germany, so in most other places in the world, what the main use of water is for agriculture. But in Germany, the main use of rivers, at least the rivers, are for navigation. And so last year and the year before, they had drought, really long drought events where the river flow went really low. And so they couldn't transport goods. And so for them, that was something that they were really worried about, because rivers are really a means of export goods. And because of that, the prices went up, because rivers couldn't be used to export goods through ships. They had to then distribute food or whatever through trucks, and that raised the prices down to the consumers. So low river flows, onset and length of seasons, heat waves, and extreme cold spells. So all of these we feel it through the water cycle. Lower quality due to temperature increase and extreme precipitation events. So higher temperature is also increasing the water quality issues. And of course, these impact on climate change on water will be effectively multiplied via the other sectors like the water, energy, food, environment nexus that we talk about. So climate change doesn't act on its own, no, it's on top of, it adds stress to already stressed systems. But the good news is the water sector can also, it can be flipped. So because the answers, the solutions for climate change also come from the water sector. So managing your water resources better is also one of the main ways of climate change adaptation, and also to increase your climate resilience. Right, so this is just one example from I think this is in Kenya. They did a study, my colleagues, in one of the river basins where they invested in soil and water conservation. Right, and what that did was because of climate change, now these high intense precipitation events are happening, but the soil and water conservation, it reduced the erosion and sediment load being transported out of this river basin. And because of that, the reservoir downstream, the life of the reservoir, you didn't have to spend as much money to first, because what happens if there's too much sediment coming from the upland areas is the reservoir fills up. And then you have to come with a dredger and take out the sediment. And there's you can't produce hydropower if hydropower is being produced from that reservoir. So as far as money goes, they saved, they could save $600,000 per year from increased power generation and avoided interruptions. And the water supply benefits were about $40,000 per year, just by soil and water conservation in the upper catchment. So this is where we will now move on to this form of adaptation. So there's various kinds of adaptation strategies, but especially in our countries. I also come from a developing country. I come from Nepal. So for our countries, this nature-based or ecosystem-based adaptation is a very viable form of adaptation. So what is ecosystem-based adaptation? So before we go into that, does anyone know? I'm sure you've heard of ecosystem-based adaptation, or not? Anyone?
Prof, I think it's making use of the environment to just adapt to the climate change, and this can be maybe making use of wetlands and all other stuff.
Yes, that's exactly right. So the definition I've written down here, maybe you can take some time to read it, but I'll read it out loud as well. So ecosystem-based adaptation is the use of biodiversity and ecosystem services as part of an overall adaptation strategy to help people to adapt to adverse effects of climate change. So you use just ecosystem services and biodiversity as a part of adaptation strategy. So we will go on to more examples of ecosystem-based adaptation. Okay, so here are some more examples. So as Aili correctly said already, it's working with nature to improve the management of natural resources. It's conserving or rehabilitating our natural ecosystems. And sometimes it's enhancement or creation of natural processes in modified and artificial ecosystems. So what is one example of enhancement or creation of natural processes? Do we know what we see in this picture here? So fish ladders, right? So this is a dam somewhere on the earth or in the world, and so they built fish ladders so that fish could also, so there's no stops in the river, no, that fish can also travel. So you're helping the riverine ecosystem to function, even though you build a dam there. Right? So it's so basically ecosystem-based adaptation. You're working with nature, you're rehabilitating natural ecosystems. I mean, Aili mentioned wetlands. I mean, that's a very important ecosystem that's been destroyed all over the world, and rehabilitating wetlands, etc. And in certain areas, then also developing systems that mimic the natural systems, like these fish ladders. So in the global context, ecosystems are increasingly degraded. Since 1900, almost 64 to 71% of natural wetland area worldwide has been lost. Because all over the world they've been draining wetlands and using them for agriculture or developing them otherwise. I mean, although 30% of global land remains forested, at least 2/3 of this area is in degraded state. Right? So so there is significant opportunity and potential to manage these challenges across all sectors. And we will talk about this in the next slides. So I want to pause here and I want to start a little discussion on anything you've heard so far, anything. So are there any questions? Otherwise, I don't know if you're listening or any, yeah, please go ahead.
Is that everything from the beginning of the lecture?
Yes, anything.
Maybe you tell us about that James Bond formula, how it relates to the global water resource at the beginning of the lecture.
Yes, so the first slide I showed you that we basically have very little water that we're working with.
Yeah.
Yeah. So that's how it is. I mean, what is your question about that? You're a little bit doubtful, yeah? Because when we think of rivers, we just see so much water. But in the global water context, most of the water is in the oceans. So 95, 96%. And that's also one of the reasons why, there's so much effort to invest in these desalination plants, that take ocean water and then take the salt out. However, as you know, as much as I do, these systems are very expensive and they create a lot of waste, and so we don't know what to do with all the salt that comes out of these desalination plants. But yeah, so water, from the earth. So after our lecture, I didn't get to do that. There's a short YouTube video that I wanted to show you, but we can watch it at the end if it works. But yeah, and it basically just tells you about, the water resources. I mean, it's not increasing or decreasing, I mean, water just changes form. So from liquid to vapor to solid, but the amount of water that we have, it's not going to increase. So we have to manage it well, yeah. But the water use, so the water availability remains the same, but the water use is growing. So, and because of climate change, this water availability is being impacted. In some places it's decreasing, but in other places it's increasing. So, you know, that's why management of water resources is so important. I mean, your area, I mean, Southern Africa, I mean, the bad news is it's getting even drier. You know? And so, I mean, I'm sure you've heard of it. So with climate change, it's already a very dry system and it's getting drier. So under these conditions, what do we do? And so you still have a lot of groundwater. But the groundwater, in some areas, the quality isn't very good. That's one thing. The other thing in your area that is, you know, of concern is evapotranspiration is very high because it's hot and dry, and this will increase, so that in certain areas, you know, even if you build a reservoir, for example, in other places like in Germany, they're thinking of building more reservoirs. I mean, for example, where I live, the city of Bonn, we get our drinking water from a reservoir. And, you know, and it's fine because the evaporation rate isn't as high. Whereas in Southern Africa or other places in the world, you build a reservoir and you put water there, but if 80–90% evaporates, then reservoir is not a good way to store water, no? Or you have to cover the reservoir. But I mean, what you have is groundwater. And so pumping out that groundwater, but the thing is to balance how much you take out shouldn't be more than the recharge rate. Because that's what they did in India. They basically, you know, they in the 1960s and 70s, they discovered groundwater. Before, they weren't really using groundwater. They were just using surface, or they weren't even irrigating. You know, there was basically rain-fed agriculture. So they used to grow 1 or 2 crops per year. But then the Green Revolution came, no? And so with this Green Revolution, it's sold as such a positive thing. But what they did was they increased irrigation. And because of irrigation, they could grow like in some areas 3 crops of rice per year. And that, of course, increased the yield. But a lot of this irrigation water was coming from the groundwater. They were pumping groundwater like crazy, so that in Western India, Pakistan, they've drawn down the groundwater so low that, you know, it'll take decades to recover the groundwater. And similar in the United States, they've used up the groundwater aquifers and drawn down the aquifers so much that, you know, it's because with groundwater, it takes years to replenish. But in other places, like, you know, in most places in Africa, the groundwater resources are still a viable resource. You haven't exploited the groundwater too much already. So if you do it, you know, conscientiously, then that's also an adaptation strategy, to use the groundwater to irrigate the crops in case the precipitation doesn't, you know, is delayed or there's a drought year. Yeah. So anything else to this topic? Or any other topics? So when we think of climate change adaptation, I mean, really, that's why I started with this hydrological cycle, because we just have to, I mean, as water managers, we have to remember the water cycle. I mean, that's our main thing. And then figure out how the water cycle is being impacted. And when you put in management strategies, you also think about how it's going to impact the water cycle. And this is what I will do. I will demonstrate in the next slides, where, you know, that we talk about. Okay. So maybe we take a break. It's not yet 10:30, but I want to get a glass of water as well. So maybe a 10-minute break, is that okay? Or do you want 15-minute break?
I think 10 minutes should do.
10 minutes is fine, right? So just go and stretch your legs, and I'll also do the same. And, you know, we don't want everyone falling asleep. And it's really unfortunate I can't be there in person because, you know, it's listening to lectures online is probably not fun, but, you know, what can we do? So, all right. So please do some jumping jacks and I'll do the same, and we'll meet at 10:35. Yeah, so 10:35, about 10 minutes, and we'll be back.
There's a question, Prof, just before the break. Yes,
okay, a question. I always welcome questions. Please, sir, go ahead.
Not a question, I have a suggestion during the break. I can suggest one or two things for your computer to adjust to the
Oh, that would be really, I would appreciate that a lot. So please, yeah, no, that would help because, you know, just looking, I mean, first of all, it's hard to teach online, and then when it's like this, it's not fun. So yeah, so could you tell me what to do? Yeah.
Okay, I will.
Sorry.
Is it a Windows computer?
Yeah.
Yes. Yes, so on your keyboard, you have to use two keys, the Windows key and P. You touch them at the same time.
Okay, so tell me what to do. Windows key. What do I do with that? Yes.
So the Windows key is four boxes, square boxes.
Yeah, I see that.
Yeah, so you touch that one with the letter P at the same time. Yeah, so it will be the corner.
Yeah, I see. It says PC screen only, duplicate, extend, second screen only.
Yeah, so you need to go to duplicate. You need to activate the duplicate.
I did that.
Yeah, so when you press on it, then maybe you need to restart the, you restart the PowerPoint again so that it adjusts to the duplicate effect.
So I close my presentation and restart again, or?
Yes.
Or stop sharing?
Yes.
Okay, stop sharing. And then I do what? I close my presentation and open again, or?
Yes.
If this works, that would be good because somehow, but is this computer, can you hear me better than the last computer, or is it the same?
Yeah, the output is fine. The sound is as good as the first.
Okay. All right. Okay, so thank you for this. So let me see if this works. So what I don't, okay, so the problem, what I find is also, when I go on presentation mode, then, you know, everything is covered, you know, so I share it. And usually when you share it, you just see it as a window, but I can still see all of you, no? But here it's like the whole screen is covered. But anyway, so when I'm sharing, I see screen window or tab, and then I see PowerPoint live.
So
which one should I do?
Screen.
Okay, and then there's entire screen, and then there's Windows and Wave browser tab.
Yeah, so preferably the entire screen.
But then you see the entire screen, no? I mean.
Then you have to pick out the window.
Okay, so now I've shared the entire screen. So what do you see?
So we see the PowerPoint. Yeah, the screen. Yeah.
Yes.
So now it is fine.
Now it's fine.
Ah, okay, now it's fine. Okay, see, what is your name so that I can thank you?
Jimmy
Okay, the
Katambo.
only okay. I'm in this ASAC, and we went through the whole selection process, no, a few guys. So, so it's nice to, so when I hear your name, I remember going through your application.
Is that one, Prof?
So I'm Jimmy Katambo.
Yeah, okay. No, I remember you. I remember your CV, and we were, like discussing. Okay. So what I will also do, okay, so give me a few minutes to, but do you see me as well?
Yes.
Ah, okay. Okay, I see that everyone is back. So I opened another computer just a minute. Okay. So is there an echo?
Yes, there's an echo.
So Mr. Computer, can you, okay, so what I did was I've opened up another computer or joined with another computer because when I go on this presentation mode, I can only see the presentation. And I also want to see you. So how do I turn off the loudspeaker?
Mute one of the devices.
But I muted.
Actually, this speaker, the volume, yeah.
Okay, how about now?
Yes, seems to be better.
It's weird because
No, it's damaged.
I think you should put the speaker on mute. One laptop speaker on mute. Because I see you have two devices there.
yeah. So what about now?
Yeah, I think now that's fine.
Okay, okay. Because this way, I see what you're seeing and I also see you because for some reason with this other one, I mean, my presentation just covers the whole screen, but now I see you and I also see the presentation and you see me twice, but it doesn't matter, I guess. I mean, yeah, you see different angles of my face, I guess. So, all right. So should we start? Are we all fine? Are we back?
Yes.
We may start.
So let me just adjust. Yes, somehow I think the management is done centrally. So when I mute or unmute myself, it doesn't really work. But oh, okay. Now you just see one of me and not two of me, hopefully. All right. So what did we talk about? We just talked about. Let me go back to the last slide. So with nature-based solutions, you're working with nature, right? So EPA, it addresses water supply through managing precipitation, runoff, storage, including soil infiltration and groundwater recharge. So all these factors are part of the water cycle, right? And that's why I started with the water cycle, because with EPA, you're looking at all these different aspects of the water cycle and you're trying to manage that. So let me go with some examples. So principles of water-related EBA practices. The first one is to protect, restore the full hydraulic response of landscapes or catchments damaged by farming or other human activities. Increase in infiltration, reduce rapid runoff, increase water storage above and below ground. So can anyone give me some examples of how we might have damaged natural landscapes and how we can fix it? Or maybe I start so that, you can. Okay, so for example, I mean, as one of our students said, part of the water cycle is when precipitation falls on the land surface. So in a natural system, what happens is that water that falls on the land surface, it gets absorbed by the soil. It infiltrates into the soil, and partly it goes to recharge groundwater or shallow groundwater. However, what we've done all over the world is if you put a layer of concrete on your land surface, what happens to that precipitation? So what happens to precipitation on concrete is the concrete blocks the water from infiltrating into the soil, so it runs off, right? So there's overland flow. It goes into the rivers and it might cause, so there's two negative impacts. One is it might cause floods downstream. So these days we're seeing a lot of urban flood events, no? And the main reason for that is because we put concrete where the water could have gone into the ground and been absorbed by the soil. So, and the other thing what happens is because water can't infiltrate into the soil, your groundwater is also not recharged. And so what do we do with these landscapes? So one example of EBA practices for urban areas is to create green spaces within cities. And what will these green spaces do? It will catch the rain that falls on those spaces and push it into the ground. Yeah? Okay, so any other example of how we might have damaged the the natural hydrological cycle and how we can repair it? All of you working on land management. I mean, another one is, just leaving soils dry, degraded. So what happens is because of climate change, our rainfall intensity is increasing. So if you leave bare soil, and then there's a high intense rainfall event, there's lots of erosion. So you're losing good soil from the uplands, and downstream, if there's a river, you're filling it up with sediment, right? And so what do we do there? You can conserve the land. No, don't leave bare soil. So that's another example. So that's one of the principles of EBA, is to restore natural landscapes. And with that, for example, if groundwater is one of your main resources of water, making sure that groundwater recharge processes happen is very important. Right? And so in many areas of the world, they've been pumping groundwater in cities, but in cities, because everything is concrete, the groundwater doesn't get recharged. And so a lot of cities all over the world, there are two things happening. One is, they have to keep digging deeper and deeper, boring deeper and deeper, because they're, the groundwater resources are getting used up faster than the recharge. And the second thing is, even the cities are, there's this word, it's basically they're sinking a little bit, because the water in the soil was also holding up. So it's like you find these areas that are sinking, like Mexico City is having a huge problem with this.
Prof, I talk about land subsidies. Land subsidies in Japan. Land subsidies. They've also experienced that situation of land subsidies where
yes, land subsidy, exactly. Yeah, so that's another issue. So here, one of the ways how you can prevent them is also what I was doing in my previous job, is building infiltration ponds. And so these ponds are basically to catch the rainfall and push water into the soil so that it also recharges the shallow groundwater or perched groundwater systems.
Prof, construction of rainfall harvesting dams.
Yeah, so rainfall harvesting is a way to, yeah, it's also an adaptation strategy. It's not a nature-based solution. It's a solution. It's an adaptation practice. But with harvesting rainfall, of course, it's a part of climate change adaptation because you're increasing your water availability by collecting water. But you're not restoring the ecosystem, no? But so it's still good, but it's a little bit outside of the nature-based solution. But it's a very important adaptation strategy because that way you don't lose the water, no? I mean, that falls in your system. So, I do that here as well. So we have, we're collecting water from our roof. And with that water that I collect, I can at least water the gardens, and it's a good way. So yes, please go ahead.
Yes, yesterday I came across this term for the first time yesterday. It's EBA, and the presenter spoke about an example in Zambia where in the past they were kind of cutting down a lot of trees to make charcoal. But now what they are doing is that they are now kind of increase production of honey, which is now kind of an adaptation. Instead of the community cutting down trees as a means of making charcoal, now they are actually making a lot of harvesting of honey. We are meant to understand that even getting into tanks per annum, which is generating quite a good amount of money. I think that's what is a nature-based, preventing deforestation, at the same time providing livelihood to the community. Thank you.
Yes. That's exactly right. So, because, I wanted to also focus on these nature-based solutions because they're relatively the cost-effective, because building dams, these constructed systems, they're more expensive. However, in developing countries, nature-based solutions are a good solution. They're more cost-effective and they're more sustainable, right? And so you reestablish. The other is you reestablish and restore natural functions of rivers, floodplains, mangroves, and other wetland environment, but with full quantified understanding of the implications for hydrology. So in a lot of places there, so I lived in Sri Lanka for a few years through my work. So, and also China is doing this as well in some of their cities. They're re-establishing wetlands, right? So that's another and then you engineer naturalistic disaster risk reduction measures with an emphasis on small scale, locally managed features as alternative or in tandem with built infrastructure. So we can also have something called hybrid systems, where you have some built infrastructure, but you also add some green aspects. So for example, when I started my career, actually, this was in the United States, we were doing a lot of stream bank stabilization. But instead of using concrete, we used geomats. And the geomats, and then we also planted a lot of grass and things like that along the streams. And what this did was it stabilized the stream banks, but it also decreased erosion and also pollutant loads, because the plants would then take up the nitrogen and phosphorus that was coming in from the agricultural areas. So these are very simple in a way. They seem simple, but very effective measures. So with water concept, do we know about blue and green water? Have you heard of what is blue and green water? So I'm sure you've heard. Yes, please go ahead. The gentleman who helped me with my computer. Oh no, this is you explained EBA at the beginning, right? So please go ahead.
I think green water is the water located in the soil that the plant can use, available to for the plant to use. That is the water that the plant can absorb in the soil.
Yes.
And the blue water is a surface water. For example, if the water located in the soil is not enough for the plant, we can use the blue water to supply for agriculture, for example.
Yeah, no, that's exactly right. And so I have written these definitions here. I mean, it was coined by this lady Falkenmark, the Swedish scientist, a while ago, just about 10 years ago. And it's useful when you're thinking about managing your water or coming up with adaptation strategies. So you think of the green water and the blue water. And so the blue water, as the gentleman, Mr. Tafila, rightly said, is the amount of rainfall that enters lakes, rivers, and groundwater. So that's your blue water. This is the main source of water that we use and manage for industrial and domestic and irrigation purposes. But only 30 to 35% of all water within the hydrological cycle is blue water, right? And the rest is what they call green water. And this is the amount of rainfall that is either intercepted by vegetation or enters the soil and is picked up by plants and evapotranspirated back into the atmosphere. So some 65% of all rain, all the precipitation that falls from the sky is cycled through the green water. So it's basically, the water in the soil and the plants, and it's infiltrated into the soil, infiltrated and percolated into the groundwater or evapotranspirated back. So when we think about water management, so we can think about the blue water management, and most governments and engineers, they usually think of the blue water management. So when you're thinking about water management or increasing water availability in an area, immediately dams and barrages and reservoirs are the first solution that governments think of. But actually it's the green water that's where most of the water is. So if you can manage your green water, then you have actually even more sustainable and bigger benefits. And so this is just a picture that shows the green water and the blue water. And you can see that, most of the water is tied to the green water. So that's in, forests, plants, landscapes, etc. And the blue water, that's in open water, it's much less. So I will take you to a case study in Nepal now. This is a study program we did a few years ago. And the problem in this system is that upland agricultural systems are rain-fed, so very vulnerable to climate change. So they have planted their crops and they're waiting for rain. So it's very dependent on precipitation. And so it's also vulnerable because if the rainfall doesn't happen, then the crops die. And the other thing was the main source of water in these mountain systems were springs. So do we know what springs are, right?
Yes.
Yeah, so in the mountains, so it was springs, and these springs were drying up. So people, their access to water was decreasing. I mean, not just for agriculture, but also for domestic use. And the existing watershed management program, they primarily focused on land management and forest management, but they didn't really think about the water aspect, you know, because these watershed programs, they're usually just about forestry. And most of the water managers, they were then just focused on building big irrigation systems. I mean, they still are. So it's like a, you know, segregation, a fragmentation of management. So one is just focused on forestry, and the ones thinking about water management, they're just focused on downstream, building downstream irrigation systems. And also the surface and groundwater systems were also managed separately. So in the mountain system, people didn't really care so much about groundwater systems. And so they didn't really know why springs are drying up. And the surface water group, they're just managing rivers and water withdrawal from rivers. So they don't think about this whole continuum of groundwater and surface water. And so the EBA approach that we introduced, which later became a very successful program. I mean, the Asian Development Bank also decided to spend, like, I think, $20 or $30 million on this. And it was from the advice we provided them, was to integrate all the natural resources, including land, trees, water, and move away from this sectoral management. Figure out where the springs are drying. And what we did was we used isotope methods to quantify where that spring water was coming from. And we identified the source of that spring water, right? And then went into those areas and rehabilitated those areas, which then caused the springs to flow again. And so this is this integrated approach. Slowing down and storing water in upland systems will allow communities to have access to water all year. By storage, we mean the whole storage continuum. So what we also did was, in these upland systems, we built this cascade of ponds, infiltration ponds. And so the ponds were used also for, you know, accessing water, but mainly to try to push precipitation into the soil and to percolate into the groundwater, because the springs were being replenished by the groundwater system. And so this cascade of infiltration ponds also helped then to decrease, you know, this gully erosion and even flooding downstreams, because you're keeping your water within the upper watershed, and also the movement of water is slow. So eventually some of the water does reach the stream, but it's a slower process. And so what happened in this area actually is the stream, you know, when it was all degraded, precipitation would occur, and there would be, you know, this gully erosion, just water overland flow, and the water reaches downstream quite fast, and there's flooding downstream. And but by doing this catchment treatments, you know, catchment conservation, we were able to keep the water within the catchment so that the flow of water goes through the soil system. And through base flow, it replenishes the stream, but the streams then are flowing longer. You know, so it's a more continuous flow of stream rather than this previous part where it was a flood and then the stream is dry.
Sorry, I have a question.
Yes.
From this case study, what were the negative impacts on the downstream, if there were any?
When it would rain, so that's the thing. So you know, the precipitation would then, it through overland flow, because the soils were so degraded, it didn't absorb a lot of water. and there was a lot of erosion and gullies, and so the water quickly reached downstream, and so there, so immediately after the precipitation event, there was floods downstream.
Oh, okay.
Yeah. And so management of both surface and groundwater is also important, especially in the management of spring systems, because in this area, some of the springs were fed by groundwater, some of the springs were fed actually by surface water because there was this interflow. But when you think of this whole surface water groundwater continuum in managing upland systems, it then increased your water availability. So this is a very, it's also a, EBA based landscape approach, right? And it's nothing new. I mean, now it's being called, EBA or nature-based solution. But already in the 1980s in the United States, there was this very good example of water for New York. So the city of New York, it was also having problems with its water availability, but instead of building big dams and reservoirs to store water or transporting water from another river to bring it in, they invested a lot of money into upstream watershed management. And that really increased, it changed the flow of the river. And that it's so that it didn't become like this flooding, and then all the water flows out of the system and then is dry part of the year, but it became this like continuous flooding river. So there's this like Catskills, I think they're called Catskills, I forgot the name, but this was already during the 80s. But even now, it's surprising that we don't think of these, solutions when we're talking about water management and also adaptation for climate change. Some of the individual approaches that were afforestation, it's to keep in forest areas, the infiltration rates are also higher, than if you have bare soil. On-farm conservation, infiltration recharge ponds. So infiltration recharge ponds, how they're different from other ponds is that some ponds, you have a layer, you seal the pond, because you don't want the water to go in, you don't want to lose the water vertically. And so they seal the ponds with either concrete or clay. But with these infiltration ponds, you don't seal the ponds. You basically have open ponds, and the main purpose is to push the surface water into the ground. And small storage tanks, here we did some sealing. So these were concrete, and these storage tanks were basically built for domestic water use. But what they also did was they covered these tanks so that the evaporative loss is reduced. And then we also did bioengineering for gully protection. So, you see this gully here, they went and, planted these plants like bamboos in this system so that the gully is filled up. And we did some social fencing, of course, where we did these treatments so that people don't come and vandalize them. Okay, so EBA can also be used for water quality. Non-point source pollution. It's been a problem since decades. Since the Green Revolution, when everyone was encouraged to use a lot of fertilizer and pesticides. So a lot of this fertilizer and pesticides then end up in our waterways. In some places less than others, but especially in developed countries, the US or Europe, where they use a lot of fertilizer and pesticides, it's even a bigger problem. But also in our parts of the world as well. because governments are also subsidizing fertilizer and pesticides. And so planting these riparian buffer strips. So along the streams and rivers, you plant, buffer strips, and these are plants. Then they create a buffer between the agricultural field and the rivers and streams. And so the nitrates and phosphorus is taken up by the plants, and so the water quality improves. And also these natural and human-made wetlands are also a very good way to buffer. So if you have these wetland areas or floodplain areas, that collect the water coming from agricultural areas, so that also gives you a protection against water quality. So drainage system, so runway. So these are two other examples. So here they created a drainage system where they also planted aquatic plants. And so these aquatic plants then treat the polluted water. And they did this, in this acid mine drainage in South Africa, as well as Heathrow Airport in the UK. So basically, these are aquatic plants that are planted, so it's natural-based solution. But these plants, then they take up the, nutrients and other things coming from, whatever. I mean, if it's a mine or from the runway, from an airport, and it treats the water, right? So EBA can mitigate human impacts of floods and droughts. So, we talked about various examples already, and I think maybe, I don't know, I asked the professor yesterday to share her slides so that we don't have so much duplication, but she didn't do so. So I don't know how much you went into this, but yeah, so floodplains, leaving floodplain areas as they are also a good way to mitigate the impact of floods as well as droughts, because in these floodplain areas, the soil moisture is still higher than other areas. So another city that I mentioned earlier, the city of Colombo, it's basically, it was just built around wetlands. So wetland cover 20% in the Colombo area, but are declining due to landfill and waste disposal. So they've just tried to increase more land to develop as housing, and some of the wetlands are just used as waste disposal. And so, but actually these wetlands are very good areas where you can store water because they ran into a lot of urban flooding problems because they got rid of their wetlands. But wetlands, like during an intensive rainfall event, can store a lot of water, and so that you don't get these flood problems in cities. Right? And so they did some calculations about if they restored some wetland, like an area of wetland, how much water they could save, and how many people would get protection against greater flood, from floods. So here they did the calculation of like over 200,000 people would be protected if only they restored the wetlands in the city of Colombo. And another nice thing about wetlands is also they recharge the groundwater because there's this connection, no? So in Wallingford, UK, instead of ever increasing the height of dikes, so we know what dikes are, no? So you have a river, and so to protect the city, they sort of build this sort of a wall, so that the water from the river can't enter the city. But the problem is, it's like they have to always keep rebuilding and fixing their dikes. So instead of increasing the area of dikes, they just created floodplain areas, or say they left in the Netherlands there is this huge program called Room for the River. So in Europe, what they did in the past is they wanted to gain more land. So they almost converted the river into it looks like a canal, so that the river just has a certain space. And the rivers were also used as boundaries against countries, so they wanted to make sure that the river doesn't keep shifting. And so they destroyed the floodplain area and built these big dikes. But now with climate change, it's becoming problematic, also because of these intense rainfall events. There's lots and lots of floods. And so now there are programs to keep the floodplain area without any development. So there's lots of new laws coming in where you're not allowed to develop floodplain areas. And in the past, they also, even if they left the floodplain area, they made it into parks or things like that, and now they're going back to the natural vegetation in the floodplains. So in the Netherlands, they've spent $2.85 billion to manage floodplains or to reintroduce floodplains, which they find is more effective and sustainable than the engineering solutions. And so worldwide, it's estimated that from the global investments, of the $800 billion that is invested in the water sector, only 5% is used for green infrastructure. So still as I said, most governments, all over the world, they just go for these construction engineering solutions. But as we saw, these natural solutions can be more effective and they're much cheaper. Okay, so the goal is, we don't have to just stick to green solutions or just stick to what we call gray solutions. A blend of green and gray infrastructure is probably what maximizes benefits and minimizes costs. Because in certain areas, you want to build reservoirs because, you need a reliable water source, especially now due to climate change and reliability, and the uncertainties introduced by climate change. But you can do it in a way where your built infrastructure has some green aspects. No? And so one example of this is, this is the modification of what, the blue water. Most governments are still focused on blue water management and building large dams, and which is fine. It's not always just green and gray. It's a blend, and to look at the balance, which is important, right? Because Australia, for instance, they had about a decade ago in the Murray-Darling Basin, they had almost 10 years of drought, but they were still able to manage because they had these big reservoirs with a lot of water stored, and so they could use this water during the drought years. So reservoirs and dams are not a bad thing, but we need to think about the balance. How to balance the green, not put just in certain cases, soil conservation, upland conservation might be sufficient. Maybe you don't need to build a dam. In certain places, you could do both, and then you get a win-win. So this is one example of what we call a hybrid system for coastal defense. Now, climate change is increasing sea level rise in a lot of areas, no coastal areas. So this is, I think, an example from the Netherlands as well. And, you know, there you have these dikes. But in addition to dikes, they're also creating these marsh areas. So they're artificially, you know, introducing marshy areas. I guess in the past, the area was marshy, but then they destroyed it, developed it, you know, built dikes. But now they're again reintroducing these tidal marshes before, you know, like in front of these dikes. So that the marshes also absorb some water and you don't need to continue to increase the dikes, and the dikes are not then damaged, because when you know, when the tides come, the marshes are like the first line of protection, and then the property isn't flooded, and the dikes are also not damaged. So this is a very nature-based solution, no, to introduce these artificial marshes, or I mean, they're real plants, but they're reintroduced. Okay, so this is all I have for today. So we can go into some questions, and I'll try to answer them, or we can go into a discussion and then maybe end a little bit early. So. And I've also, I mean, if we want to talk about vulnerability to climate change or any other topics on water management, I mean, as I said, I've worked in water management since the last 20 years, working with different governments in different countries and continents, with the World Bank, with Asian Development Bank, etc. So we can have a more open discussion as well. So are there any questions or any items you would like to discuss? So IWRM, so all of you are doing your PhD study in IWRM. So what are some of the constraints that you find with IWRM?
Can I say something?
Yes, please. Yes.
Yeah, sorry. While people are still thinking about their challenges and IWRM, I also wanted to just share the experience from Cape Town, from Western Cape, where I think it's one of the sort of response measures to the drought as well, and to try and see how they try and unlock more water. So in the Western Cape, they've got the challenges of alien invasive plants, and these are quite a lot, especially on the catchments. And the problem that they pose is that they are extracting water from the ground, and also since they don't have any predators or whatever is feeding on them, then they add fuel load. So when wildfires occur, then it really gets out of hand to control and manage. And as a way to sort of, and as you know, alien invasive plants, like they really guzzle water from the ground. So as a way to try and address that problem, they started with the water fund, where they are bringing stakeholders both from the upstream and downstream to collaborate financially and in kind to clear the alien invasive plants at the catchments. And I think this has been one of the successful examples of the water fund that's also bringing the private sector and government and the local communities to work together towards identifying a solution. So what happens is that the local people are employed to do the clearing. but the planning is such that it's in line, the planning for clearance and all is in line with maybe the strategic plan for the municipalities and the province as a whole. And I think they were actually, from the studies that were undertaken, I think they were actually able to improve people's livelihoods, and they were able to, and they are now starting to sort of experience like the return on investment in terms of the water that they're managing, the increase in the volume of water that's flowing in the rivers. I think about 3-4 years later. And yeah, and I think this is also contributing to the aquifer recharge, increase in the water table, etc., amongst other issues, amongst other benefits that they are now starting to reap. So yeah, I thought that's also another good example of EBA.
Yeah, no, it's a very nice example. And that's why I started this lecture with the water cycle. So as water managers, we have to always focus on the water cycle. And so, you know, this example you brought forward, so what this plant invasive species was doing was probably, you know, using a lot of the water, and it evaporates. You know, and so a lot of water is lost from the system. And so this has happened all over the world. I mean, I remember in Asia, someone thought they wanted to, so, you know, in my country, Nepal, the Australians, they had this plan to reforest, you know, the mountains, because they thought, okay, that would be a good idea, which is a good idea. But the tree they chose was eucalyptus. And eucalyptus, as we know, it also uses a lot of water and evaporates. So what happened was all these streams, so they went and they spent millions of dollars in reforesting. We're using eucalyptus, and then the streams are going dry. And then everyone is wondering what's going on. And then they finally figured out that this tree was basically using up too much water, evapotranspirating it, and the streams are going dry. And so that's why when we introduce any sort of treatment or management of the landscape, it's very important to think about, you know, the water cycle and how it's impacting the water cycle. So here in this case, as was explained, evapotranspiration increased because this invasive species was just using up too much water. Maybe the roots even went into the groundwater and was drawing up the groundwater. So even the groundwater is being reduced, and maybe the plant is also useless, so that you can't even eat it or, you know, use it for any. So yeah, so that's so I think there was this one case study that I heard of where what they did was then they cleared a lot of the bush of this plant, of the shrub. It was a shrub, and then they used it for biomass production. And so they were actually getting something out of, you know, clearing the bush and then or that shrub and then producing biomass. So that's, yeah. That's a good example. So yeah, so just planting something somewhere or letting invasive species spread, it affects the whole water cycle, and then which then affects your water availability. You know? And so it's, yeah. So always go back to the water cycle, I would say. So thank you for this example. So anyone else? There's a hand up behind. Yes, please, sir, go ahead.
Yes, Prof, I direct your attention on slide 25. Yeah, so slide 25.
This one?
Maybe for me it is, I took a screenshot, so on the corner it's written 25, but then it's the one that shows the buffer strips.
Okay.
Yeah.
Yes, you know, I worked on this establishing buffer strips back in before climate change was even an issue, long time ago. But we were actually planting buffer strips in Iowa, where we used prairie grass and silver maple and that kind of stuff, and then quantifying, the pollutant loads. But yeah, please go ahead.
So you said earlier on in the discussion that the buffer strips are made between rivers. So I would like to see which one is the river there. Then also on the right-hand side, you have the graphs. So I don't understand the illustration for the graphs.
Yeah, so this was actually research that I did. When I did this was my master's, so you can imagine how long ago this was. But anyway, so this work was done in the 90s, and I finally published it in 2002, and it's one of the most cited papers that I wrote. It's like over 300 or something citations. But what you see here is the infiltration rate. So what we did, so I was part of a project where, in Iowa, in the US, even now, you have these large agricultural areas and that go right up to the stream. And the stream is completely polluted because, like I said, they fertilize a lot, and all this fertilizer ends up in the stream. And so what we did was we planted these buffer strips, and my job was to measure the effectiveness of the buffer strip. So we planted silver maple trees, we planted a grass filter, we planted switchgrass, was a kind of prairie grass, and then the bean and corn was basically the agriculture. So I went and measured infiltration in different seasons, so June, August, and October, November. In these riparian zones, which had silver maple, grass, switchgrass, to try to see which plant offers the highest infiltration. And of course, what we found was the silver maple, where we planted these silver maple trees, the infiltration was the highest. And that then was good because the water coming out of the agricultural areas then infiltrates into the soil and is taken up by plants as nutrients. Right? And so we were just testing what kind of plant to plant in the buffer strip. So silver maple was the best. Switchgrass, which is a prairie grass, and even regular grass was better than switchgrass, because at that time, everyone thought, okay, they should plant prairie grass because the natural system, everyone likes prairie grass because it flowers and all that. But yeah, so that's what this one is saying. And of course, in the bean and corn and pasture, where they have cows grazing right up to the stream, the infiltration rate is the lowest. Yeah. And this is cumulative infiltration, yeah.
So it's the river is between the two strips that I'm seeing on the graph.
Yeah, yeah. So the river is that little, looks like a snake. It's a small stream. It was a small stream, but it's basically all these small streams that, where the pollutant, it carries all the pollutants, and going from these agricultural areas. So what I measured was nitrate, phosphorus, at that time atrazine, because that's what they were using in the pesticide, as well as sediment. From the streams. And then I also measured the infiltration rates in the riparian zone with these different kinds of treatment, with grass and switchgrass. So as to recommend how they should develop the riparian zone. So our recommendation from this study was silver maple or just grass filters are also good. And it was much cheaper than, other like switchgrass at that time. Yeah, so Yeah, and another thing is like with climate change, there is a lot of concentration, focus on water availability, you know, changes in water availability, but there isn't still a lot of studies on what's happening with the water quality, because a lot of places, you know, the water quality is also degrading, also because of climate change, because of these high intense rainfall events that we're experiencing. They're really you know, polluting the waterways as well. And so this is then a nice EBA, so, you know, nature-based solution to protect your rivers. So any other question? Okay, so I'm actually involved in the SGSP program, in that our center is the German partner. So when all of you come to Germany, so, you know, we will see each other, and we're planning an education tour, I mean, exposure visits for you. We're planning a workshop for you as well. So I'm really looking forward to all of you coming to Germany. And if there are any issues that you might have with your German supervisor, so you can I mean, of course, you know, you've been doing it through the SGSB program, through Renee and Patrina, and that's fine as well. But, you know, when you're in Germany, then we'll be responsible for taking care of you. So I'm really looking forward to seeing all of you. So just last week, we developed a proposal for you to go on some exposure visits here in Koblenz. We're based in Koblenz, so we'll get you all together, and we've hired a bus, and we'll see, I mean, what all we can include in the tour, but I'm really looking forward to welcoming you in Germany.
Thank you very much.
Okay, then I think we're done for today, and a little bit early is always nice, I guess, for you. Students are always happy if I end early rather than late, so. But I will send you a link to a publication and also just a very simple video on water balances. It's not even a scientific video, but I really, you know, it's like when people are talking about climate change adaptation or water management, I mean, you forget the water cycle. I mean, always think of the water cycle, and then and then think of how your management option or climate change adaptation option will impact the whole water cycle, you know, and then yeah. So that's all for today, and I will sign off now, and thank you very much for attending, and it was great, and it would have been nicer if we could have seen you in person. And hi, Renee, Petri. Oh, I didn't know you were also sitting there the whole time, so great.
Oh, we had the whole lecture. We always make a point of it.
That's great. Yeah, no, I don't know, like
there
was
the
this
background.
confusion because this Professor Gizau, he asked me to just talk about adaptation, and that's why, you know, I'd prepared this lecture. But then in the poster, it was like modeling. I mean, I could have also done a lecture on modeling, but maybe at some other point, you know, or maybe when they're here in Germany, we could do something on. Because I've worked quite a lot with SWAT and WEEP and, you know, these hydrological models. But anyway, so maybe another time then, yeah.
No, I think on behalf of the Secretariat and the SGSP students, we really want to appreciate you, Dr. Luna Bharati, for making the time to prepare this particular lecture and to engage with our students and share the knowledge and insights and experience that you have. I think it has been a very insightful half-day engagement, and there are key lessons that we all walk away with, especially regarding ecosystem-based approaches to the planning and management of water resources. So we quite appreciate your insights. If there are any additional resources that come to mind, do not hesitate to share this with the students, and we can also share their group email in Secretariat, because we have a repository where all this material is also made available so that they can always refer back to it. And we, in the same fashion with the rest of the facilitators, students, you are quite free to engage the respective facilitators, Dr. Bharati in this context. If you've got additional questions, either as a group or as individuals, this is just the beginning, but we believe the relationship and the conversation continues, especially when you reflect into your own work that you're doing in your research, and some of the aha moments as you're planning and executing your research plans. So Dr. Bharati, thank you so much for making the time. You are no stranger to SGSP. ICWRGC is actually a partner in implementing the program. So these are your students. Anytime you need to engage with them, Secretariat is at your disposal. Please do not hesitate to reach out, but we quite appreciate the time. I think this whole week was very insightful. Our students should be exhausted, but they are walking away richer in terms of knowledge and experience than they were before the seminar series began. So thank you so much for making the time, and to Dr. Mabuku for always being the force behind the scenes, Tafila, for ensuring that you are co-facilitator throughout the week, and for those that even shared their laptops so that you have got constant access. We really appreciate you, and we really want to wish you a restful weekend ahead and exciting week to come next week. So let's just give Dr. Bharati a round of applause in appreciation of the time.
Okay. Well, thanks, Rennie. And yeah, it's always nice to see you and interact. I mean, okay, so all right then, lunchtime for everyone, and I wish you a nice day, and we'll be in touch. And as Rennie said, I mean, don't hesitate to contact us. I will send, I think the lady who sent me the link, Ronelle, some of the reading material for students for reference, because then she can just forward it, and it's probably easier that way. So yeah.
Right, I agree. And Ronelle, thank you so much. You know, there are always soldiers behind the scenes. Ronelle, Christine, we also appreciate your support. Have a good day, colleagues, and goodbye for now.
Yeah.
Thank you very much. Goodbye.
I think I've got right on this one. Some people never do.